Let's have a look now at an example that relates electric field and electric potential. So let's say that we're given that the electric field in a region of space is that the x component of the electric field is 5,000 times the coordinate x, and the units of electric field are volts per meter, and x is given in meters. First thing we're tasked with is to graph the electric field as a function of x. In between x is plus and minus 1. So I'll say this is minus 1 for x, I'll say this is plus 1. If we look at the shape of our graph, we see that Ex equals minus 5,000x. This tells us that our graph is linear, and the slope of the graph is minus 5,000. Oops, I don't know where that minus came from. Electric field is 5,000 times x. I wrote a minus here for some strange reason, but that's positive. So the slope then is 5,000. If we wanted to draw that graph, it would just be a straight line with a slope of 5,000, something like this. Okay, part B. Find an expression for the potential V at position x. Let x equal 0 at the origin. So this last bit is giving us a reference point. Let's write down how electric potential and electric field are related. We know that delta V is minus the integral of E dot ds. So these are the parallel parts multiplied. This is the x coordinate, and this is an x position, so that's going to be the same as minus E dx. Those things are in the same direction. So let's fill in what our Ex is. That's 5,000 times x dx. We're going to integrate between some initial value and some final value. You can take your 5,000 outside. The integral of x is x squared over 2, so that gives us minus 5,000 times x squared over 2, and that's evaluated at x final and x initial. I'm running out of space a little bit here, so I'm just going to move up here. So delta V is V final minus V initial, because that's what a delta function is, equals minus 5,000 divided by 2, and that's 2,500. That's going to be times x squared. Now hang on, I don't want to drop my minus sign. That's going to be times x final squared. Take away 2,500 x initial squared. And since we subtract this term, when we subtract our negative, we get a positive. Now let's put in our initial conditions. If x is equal to 0, normally that's what we say the initial point is, our potential is equal to 0. Okay, so those guys are going to be 0. And then typically, instead of saying x final, we would just say x, and instead of saying v final, we would just say v. So our final expression would be v equals minus 2,500 times x squared. If we wanted to plot that guy, it's going to be parabolic because we have an x squared, and it's a negative, so it's going to be upside down. And that's x equals 1 and x equals minus 1. So the graph would look something like this. Okay, then every time I graph something by hand, I normally also do it on Excel, so I do have that done here. Let's have a look at that Excel graph. I've got the two graphs on the same thing. Let's also think a little bit about a bit of a summary and how the electric field and the potentials are related, particularly when we think about graphs. Well, the relationship between potential and field is that the change in potential, delta V, is minus the integral of E dot ds, which would be minus the integral of the s component in the s direction with respect to the x direction. And then the flip side is that the s component of electric field is minus the derivative of potential with respect to s. I assume you've seen this symbol before. It means a partial derivative. So it's like a D, but it's a bit curly. It's called die. So it means to get a component of electric field, you take the derivative of potential with respect to that variable. If we were doing the x component, we would take the derivative with respect to x. The y component would be the derivative with respect to y. So let's think about that in terms of our graph. What is E in terms of the graph of the potential? So that's a good question, and it's always something good to think about. So the derivative of a function is the same as the slope of the tangent. And then we have a negative here, so that's telling us that the s component is going to be negative of the slope of the potential, and you take the slope at a tangent line. Okay, so ES is equal to negative of slope of potential graph. Let's just look at a couple of spots on our graph here and see if it makes sense. Let's look at 0 first, where x equals 0. So at x equals 0, if we wanted to find the slope on the graph, so the orange is our potential line, if we wanted to find the slope, we would draw a tangent. And our tangent would be a horizontal line. The horizontal line would have a slope of 0. So at the origin, the slope of tangent is equal to 0. So at x equals 0, the electric field equals 0. And that matches our equation for electric field, so that's good. We can do a couple of other places. If we were out here, and we won't get a value here, we see that the slope of the tangent here is positive. The electric field is the negative of the slope, so the electric field would be negative. That matches our equation too. If x is negative, E is negative. We could do likewise down here. I won't draw it in because it'll mess up the graph. But over here the slope would be negative, so the electric field would be the negative of a negative. Our electric field over here, when x is positive, and that matches this equation, so that's good. Then the last little bit, we're looking at a graph of a curved potential. If your potential was linear, then you don't have to do the slope of a tangent. You can just straight up do the slope. And that would be your familiar rise over run method from high school. Okay, I think we have time on this video to do one more example before we move on. Let's say that we have, make sure I'm on the screen here. Let's say we have the electric potential in some region of space, and it's given by V of x, y, z. So that means all three of our coordinates matter, x, y, and z. It's given by some constant times x squared minus 3y squared plus z squared. X, y, and z are going to be in meters, and ultimately our potential is going to be in volts. So part A asks us to find an expression for the electric field. So let's see how we find the expression for the electric field. When we wrote down the relationship between field and potential, one way I wrote it down that was E is minus the gradient of V. What this means when you try and break it down into something practical, a way to solve your problem, is that the x component of electric field is minus the derivative of the potential with respect to x. The y component is minus the derivative with respect to y, and the z component is minus the derivative with respect to z. Let's see how we do that. So for the x component, we do minus di by dx of a times x squared minus 3y squared plus z squared. To do a partial derivative with respect to x, it means we treat x as our variable, but we take everything else as constant. So in this expression, we treat x as our variable because we only care about the change with respect to x, and we take y and z to be constant. So the derivative of a times x squared is going to be a times 2x, and don't drop that negative sign, so I get minus 2ax. The derivative of minus 3y squared is 0, and the derivative of z squared is also 0, because we're treating y and z as constants. Okay, let's do the y and z components, and then we'll put it together with our expression up here. Our y component is we take the derivative of potential with respect to y, so minus di by dy y of ax squared minus 3y squared plus z squared. The derivative of ax squared with respect to y is 0 because we take our x as constant. The derivative of minus 3y squared is minus 6 times y, and then we still have our negative here, so we have plus 6 times y, and the derivative of z squared is going to be 0 because we treat z as a constant. Okay, last derivative, minus di by dy z of a times x squared minus 3y squared plus z squared. The derivative of ax squared is 0 because there's no change with respect to z. The derivative of 3y squared is 0 because there's no change with respect to z. And the derivative of z squared is 2z, and don't drop your minus sign. Okay, so now what we have are the x, y, and z components. Oh, I dropped my a. Oops, I did that up here too. So the a comes in as well. So now to write down our electric field, we've got our components. Now we just have to write it as a vector. So the gradient can also be written as minus di v di x in the x direction, minus di v di y in the j direction, minus di v di z in the k direction. So our x component is minus 2ax. That's in the x direction, so it gets an I hat. Our y component is 6ay in the y direction, so j hat, and our z component is minus 2az in the j direction, so it gets a k hat. So there's our expression for our electric field when we know the potential. And that's part A. Part B says that we know how much work is done if we move from a place where x is 0, y is 0, and z is 0.25 to the origin. So we know how much work is done on a 1.5 microcoulomb test charge, and we want to find the constant A. If you're not totally sure how to do this right off the bat, why not start by writing down things you know about work? And one thing we know about work is that work is minus the change of potential energy. So now we're trying to solve what is A, which is the super question. So we know that work is minus the change in potential energy. Since we have charges moving around, this is electric potential energy. And we know that electric potential energy is Q times V. So we can relate the work done on our charge to the change in potential and the charge itself. So we know what we're going to fill in for Q, 1.5 times 10 to the minus 6. We know what we're going to fill in for work, 6 times 10 to the minus 5. The last bit of the puzzle we need is what are we going to fill in for delta V? Well, we know our V functions. We can fill in our initial and final positions, and that'll give us our initial and final potentials, and we can solve for our delta V. So delta V is V final, take away V initial. V final is at the origin, so that's V of 0, 0, 0. Take away V initial, which is at 0, 0, 0.25. Okay, V at all zeros is A times 0 squared minus 3 times 0 squared plus 0 squared. Okay, that's all 0. Then we're subtracting our potential at our second place, so that's going to be A times x equals 0, so we've got 0 squared, minus 3 times y is equal to 0, so we got 0 squared, plus z squared, but z is 0.25. So that gives us for our potential minus, okay, so I just got my brackets here so I don't lose track of my minus signs. So I've got that whole term is 0, that one's 0, that one's 0. Got minus a times 0.250 meters squared, which is minus a times 0.0625 meters squared. Okay, this is what I'm going to plug in for my delta V, and then probably you notice that the only thing we don't know is A, so we'll be able to solve for our A. Let's fill in our work. 6.00 times 10 to the minus 5 joules equals minus Q, 1.50 times 10 to the minus 6 coulombs, times delta V, which is minus A, times 0.0625 meters squared. Okay, I think I'm good with my exponents. Now I'll solve for my A. When I solve for A, I get 640 joules over coulombs times meters squared. Joule over coulomb, that's just a volt. 640 volts over meters squared. If we take a moment to think about our units, our V was some constant times a whole bunch of positions squared. So all these guys were meters squared. We wanted this to be in volts, so this has to be volts per meter squared. So that shows us that we've got the right analysis done for our part B.